Welcome to the Math Advantage podcast. I'm Dr. Silas Vane, and today we're looking past the formulas to find the logic, risk, and strategy that run our world. Whether you're in the classroom or at the kitchen table, let's get started.
What if I told you a single test, a single headline, or a single app alert can completely change how you feel about a person, a school place, or a health decision? Imagine your child comes home and says, "I got flagged on the school app," or you see a viral story about a miracle exam technique. Instantly your heart races, your questions multiply, and suddenly the unlikely feels urgent. This is about real people and real choices, not symbols on a page.
Here's the human bit. We react to the signal without asking how often the thing we're worried about actually happens. That mistake turns rare things into everyday terrors. Don't fear the decimal. The maths helps us be sensible again.
So, what's the big idea? Plain English first. A base rate is just how common something is before you get any new information. Updating your belief means taking that prior sense of how common something is, then adjusting it when you see a test result, a headline, or an app alert. Think of it as starting with the map, then changing your route when you see new roadworks. The map is the base rate. The roadworks are the new evidence.
When I worked on the trading floor dealing with fraud detection, we used exactly this thinking. We had a system that flagged suspicious transactions. It was very good at spotting odd patterns, but the base rate of actual fraud was tiny compared with the number of transactions. So if you block every flagged transaction, you create massive user frustration and cost. The decision wasn't, is this flagged? The decision was, given how rare fraud is, how much should one flag change our belief that this is fraud? That operational research insight, that decisions must balance detection and cost, is the same advantage you get when you understand base rates. The variance is where the story is.
Now, an everyday analogy. Baking a tray of cookies. Imagine 10,000 cookies. 2 of them are lemon-flavored by accident. You have a detector that says lemon 99% of the time when a cookie is lemon, and 99% of the time it says not lemon for a normal cookie. If your detector flags a cookie as lemon, what's the chance it actually is lemon? Many people hear 99% accurate and think nearly certain. But because only 2 cookies are lemon, most flagged cookies will still be plain. That mismatch between how accurate a test sounds and how rare the thing is, that's the trap base rates save you from.
Here's the practical mental checklist I use and that you can silently run when you see a dramatic result. 1. Ask how common is the thing before any tests. That's your base rate. 2. Ask how good is the test or signal. Does it miss things or cry wolf? 3. Combine them. If the thing is rare and the test imperfect, the chance it's real is lower than you think. Think like a statistician. Start with the map, then incorporate the new view.
A small PhD polish for the curious. In operational research, we call the trade-off between false alarms and misdetections a receiver operating characteristic, and decision thresholds depend on the relative cost of errors. Put simply, the right threshold in the city might be higher than at a hospital because the costs are different. That's the advantage. The math tells you where to set the threshold to make the best decision for your context. The math checks out.
Student challenge. Imagine a school screening app that flags 1% of students as at risk for needing extra support. The app is right 90% of the time when it flags a student who truly needs support, but 10% of the time it flags students who don't. You see your friend was flagged. What would you do next? Would you panic, ask for evidence, or change your view about the school's support system? Hold that answer. I will reveal how to think about it and the numerical answer at the end of the episode, and you can find the full solution in the show notes. Parent prompt. At dinner tonight, you don't need to teach Bayes to your child, but you can spark curiosity. Try this line. Before we jump to conclusions, what do you think? How often does that actually happen? Or, if our detector is very picky, how could we check if it's correct? A quick home activity. Flip a coin 20 times and write down surprised reactions when you get long runs. Then talk about how surprise doesn't always mean something strange is happening. Focus on encouragement and wonder, not correction. Say, "Great question. Let's figure it out together." That's the win.
Teacher takeaway. Students often mix up P of A given B with P of B given A. In plain terms, they confuse probability of disease given a positive test with probability of a positive test given disease. That confusion is the heart of the problem. A ready classroom question. In a school of 10,000 students, 50 have condition X. A test detects condition X correctly 95% of the time and gives a false positive in 2% of healthy students. If a student tests positive, what is the chance they actually have condition X? Use a frequency tree or 2x2 table to make the base rates concrete. This works perfectly for GCSE probability revision and A-level statistics decision modules. It's especially good for A-level statistics paper 3 style questions on decision-making and risk. For higher achievers, stretch by asking them to produce a cost matrix. How would policy change if the cost of missing a case doubles?
Common misconception. Students think accurate test equals useful test, regardless of prevalence. The lesson: always contextualize accuracy with prevalence. Resource note. The downloadable pack contains the classroom question, worked solution, marking points, and extension tasks for fast finishes. And a quick reminder, this discussion is about decision maths, not medical advice. If you have personal health questions, consult professionals.
Right. Time to resolve the student challenge. Go back to that school app scenario. 1% of students flagged, test is 90% sensitive for true need, and flags 10% false positives. If you imagine 10,000 students, 1% flagged means 100 flagged. But how many of those are true positives? If the true number needing support was, say, 50 in the school, the math shows many flagged students will not actually need additional support. The practical move is to combine checking background rates with quick follow-up checks rather than immediate action. Details and the numerical breakdown are in the show notes, so check that if you want the full worked numbers.
One sentence advantage, tracking base rates and updating sensibly gives you the advantage of making calmer, better decisions when a rare event suddenly looks common. Here's the thing. It stops panic and starts sensible action.
If you found this useful, subscribe to the Math Advantage for more episodes like this and download the resource pack in the show notes. It has the student challenge solution, classroom resources, and extension tasks for high achievers. Share this episode with a teacher or a parent who could use a quick logic boost. Thanks for listening to the Math Advantage podcast. You can find today's student challenge and teacher takeaways in the show notes. Until next time, keep thinking mathematically. Stay curious.